Welcome, everyone, to this explainer. Before we even think about touching a keyboard to write computer code, we have to construct a solid foundation. Think of it like building a house. You wouldn't just start nailing boards together, right? You need a blueprint. And in computer science, before we write a single line of actual code, we must construct a rock-solid logic blueprint through what we call the pre-programming phase. This phase has 5 critical steps, and by the time we're done today, you'll know exactly how to map out a perfect program before you even start coding it. Let's get into it.
Here's our roadmap for today. We'll hit problem-solving basics in PAC, structuring with hypo and IPO, visualizing with flowcharts, writing pseudocode, the 4 logic structures, and wrap it all up with a final review and takeaways.
All right, part 1, problem-solving basics and PAC. Okay, let's dive right in. At the very heart of computer problem solving is the algorithm. So what exactly is it? Simply put, an algorithm is a step-by-step procedure, an action plan really, that processes inputs to produce an output. If a problem can be solved by a set of step-by-step actions, a computer can handle it. This algorithm is the absolute literal foundation of our blueprint. To actually write that algorithm, our very first step in the pre-programming phase is analyzing the problem using what's called a problem analysis chart, or PAC. Think of the PAC as a way to gather your raw materials. For a simple payroll problem, our PAC is neatly divided into 3 columns. First, the data provided by the user, in this case, hours worked and pay rate. Then the processing required, multiplying those hours worked by the pay rate. And finally, the output we need, which is the salary. It's just a clean, simple inventory of what we have and what we need to do.
Moving right along to step 2, structuring with hypo and IPO.
Now, to handle really complex problems, we bring in a hierarchy input process output chart, or just hippo chart for short. Because let's face it, big problems require big programs, so we use a top-down method to divide the processing into smaller, manageable subtasks called modules. Notice how the main module at the top, the payroll control module, dictates the flow to all the other numbered modules beneath it, like calculating gross pay and net pay. Programming that uses the specific approach of dividing a problem into subtasks is called structured programming. All right, quick exam prep call out for you. You are absolutely going to be asked about the difference between a PAC and an IPO chart. Here's the key to remember. The PAC just outlines your basic data, processing, and output. But the input process output, or IPO chart, combines the info from your PAC and your HIPO chart. It extends the analysis by detailing the specific input items, pairing them with their specific numbered processing modules, and defining the final output results. Let's actually walk through an IPO table so you can see exactly how this works in action. Check out how the subtasks from the Hippo chart are now perfectly assigned. Our inputs like hours worked and pay rate are linked directly to numbered processing modules, like module 1100 to enter hours and module 1000 to calculate gross pay. All of these structured modules eventually lead us logically straight to our output, the net pay. It's just incredibly organized. Next up, section 3. Visualizing with flowcharts. A flowchart is quite literally the blueprint of our logic, and the best part? It's completely independent of any specific programming language. Just like an architect's blueprint, it uses a standardized visual language. The International Organization for Standardization provides these specific shapes for us. We use an oval to indicate the start and end of the logical flow. A standard rectangle handles processing and calculations. The parallelogram indicates input and output data. The diamond, and this one is crucial, that's for decision-making based on a true or false condition. And finally, a double-lined rectangle is used to call upon those subprogram modules we just talked about. Let's bring this down to earth with a highly relatable everyday example. Taking an umbrella. We start with our oval. We use a parallelogram to ask for input. Is it raining today? But here comes the diamond shape. This is our decision point. It asks the condition, is it raining? And creates a literal fork in the road. It forces a yes or no path. If yes, the rectangle process says, take an umbrella. If no, the process says, leave umbrella at home. Both paths then lead down to the end oval. Simple, perfectly logical flow. Now, let's look at how these exact same shapes can handle some math, like a loop finding the sum of the first 50 natural numbers. We start by initializing our sum and our number n to 0. Then we hit a process rectangle that increments n by 1. We add n to our sum. Then boom, we hit the diamond decision. Is n equal to 50? If no, the arrow loops all the way back up to increment n again. This logical loop just keeps repeating until n finally hits 50, triggering the yes path to print the sum and end the program. All right, section 4, writing the pseudocode.
So what happens when we translate those shapes into text? We get pseudocode. Pseudocode is essentially imitation computer code. It's a set of instructions in a descriptive form that mimics the logic of a program, but without being tied down to the strict syntax of a real programming language like Python or Java. It really is the perfect readable stepping stone between our visual flowchart and writing actual code.
What's really fascinating here is just how directly a flowchart maps right over to the pseudocode. Think about a visual flowchart with modules for reading inputs, calculating pay, and printing. Then look at the pseudocode algorithm. You can see how a read parallelogram perfectly translates to the text command RAID hours pay rate. The processing rectangle for calculating pay simply becomes the text equation gross pay equals hours worked times pay rate. The visual shapes are directly dictating the written logic. It's a one-to-one translation. Moving into Section 5, the 4 logic structures. To build a truly efficient computer solution and to keep us from constantly rewriting identical processes, we rely on 4 fundamental logic structures. Number 1, sequential structure, where instructions execute one after another. Number 2, decision structure, which branches paths using if and then logic. Number 3, loop structure, which executes a set of instructions multiple times. And number 4, case structure, which executes one specific set of instructions out of several different available sets. Let's contrast those first two. First, we have the sequential logic structure. This is your straight line execution. Instruction 1, then instruction 2, then instruction 3. No detours, no variations. Then there's the decision logic structure. Here, you hit a condition, and the path physically splits. You're going to execute either one set of instructions or the other, based entirely on whether that condition is true or false. Here's that decision logic in action, calculating overtime pay using what we call an if-then-else instruction. The condition is if hours are greater than 40. If that's true, we follow the then branch, which calculates pay at a time-and-a-half overtime rate. But if the hours are not greater than 40, we follow the else branch, calculating pay at the standard rate. The else part is technically optional in programming, but here it perfectly catches our standard 40-hour workers.
Okay, I want to pause right here for a major wait, what moment, because this is a classic exam trap regarding repetition structures. Look really closely at the difference between a while loop and a do while loop. A standard while loop checks the condition first, meaning if the condition is immediately false, the loop might literally never run. But a do-while loop processes the body of the loop first before checking the condition at the end. That means a do-while loop is mathematically guaranteed to run at least one time no matter what. Do not forget that distinction. And finally, Section 6, final review and takeaways. All right, lock this in your memory for your assignments and exams. We've got a 5-step pre-programming phase. Analyze the problem with a pack. Develop a top-down hippo chart. Detail the specific modules in an IPO chart. Draw out your structural flowchart using standard shapes. And finally, translate it into descriptive pseudocode. And remember, all of that logic is built using just 4 core structures: sequential, decision, loop, and case. So, you now know how to map out incredibly complex, efficient instructions for a computer using a highly structured blueprint. But I want to leave you with a final thought to really test your understanding. If you had to use these exact tools, the diamonds, the rectangles, the loops, and the if-then decisions, to draw a flowchart for your own morning routine getting out of bed, where would the biggest loops and the most difficult decisions be? Think about it. Thanks for joining me on this explainer, and I'll catch you on the next one.